Hello, welcome to the life cycle of a star. So this PowerPoint is for Key Stage 3 and beginning Key Stage 4, so GCSE. I am Laura Lewis. Let's look at the learning aims. Oh, got a bit of an animation there first. Look at the learning aims. So, number 1, describe life cycles of stars of various sizes from their formation to their death. Number 2, understand how nuclear fusion forms elements and creates energy for the star. And number 3, how to answer questions on star life cycles. Okay, so let's have a look. So the Hertzsprung-Russell diagram is this diagram. It's a very pretty diagram, but it shows a lot of information too. So let's have a look at the main features of it. So we've got down here the white, so these are all stars, okay, there's no planets or anything else, they're all types of star. So we've got the white dwarf stars down here. Sirius is in the sky in the winter time. Procyon is its neighbour actually in the sky, so they're quite similar types of star. We have the main sequence. So as we'll talk about a bit more detail later, these are stars which are undergoing nuclear fusion in their cores. So the sun, it's quite small here, but the sun is there. Okay, so the sun is kind of a medium-sized star on the smaller side, which is on the main sequence that's undergoing nuclear fusion. There's a pretty average star. Then we've got the giant stars. If you look at these names that are up on the internet, they're all stars you can see in the sky. Okay, pretty much all year round in UK. Okay, so Betelgeuse and Antares. So definitely in the winter time, you can see some of these stars in Orion. And you have blue giant. Notice all different colours too. So the colour actually represents what temperature it is. And it's the colours of these stars in real life. So these are the colours of what the stars actually are. So the bluer the star, the hotter it is. So you see a blue star, the hotter. So this goes from, this axis is the other way round to a normal axis. So this axis goes from very, very hot to cooler stars. And again, the sun's somewhere in the middle towards the cooler ones. So the sun's here. And if you look underneath, these have got letters associated with them. It's a G2 star. So we call a G2 yellow dwarf. So it's on the smaller side. So when you get a dwarf rabbit or something, it's like a smaller version. So it's a little bit of a smaller star. Okay, not the smallest, as you can see lots of stars are smaller than it, but it's one of the smaller ones. Okay, so star formations, how do we get to stars? This is photograph, it's a photograph, not a painting. It's the Orion Nebula. So again, that's in the sky in the winter time in Orion. Okay, so there are huge clouds of dust and gas in space. So nebula is one, and that word there is nebulae, that means more than one. So there's more than one out there. That's just an example of one, the Orion Nebula. It's so bright you can see it a little bit with your own eyes, like a smudge in the sky. You can actually see the Orion Nebula. So stars are forming in a nebula. That's because gravity is pulling the dust and the gas together to form protostars. So before they are a main sequence star, they're a protostar. It's actually emitting light due to energy being converted from gravitational to kinetic energy and light in the gas. Also some thermal too. Okay, that's why they actually shine, is they emit thermal and light energy. Okay, and you can see the little blue stars in the nebulae. These are stars that are forming. So you actually see them forming in the nebula today. That's how we know about it. You can actually see them with quite obviously powerful telescope. You can see the stars forming, but you can see them. Okay, so yeah, they can be seen inside the nebula. So when we say big, these nebulae are light years across. They're much, much bigger than the solar system. They're absolutely huge. Okay, these nebulae. Think about how big the sun is. Okay, that's a star. So think about, it's probably a similar size to our sun, and how big that nebula is compared to it. Okay. So the main sequence is called. So stars form at different masses, just how much gas was around them at the time. Okay, so some form as red dwarfs, so they're much smaller than our sun. Some are hundreds of times bigger than our sun. So they're bigger in their size, but their masses are only about 30 times. There's a limit, like a physical limit they can form at. Okay, and stars are considered to be on the main sequence once nuclear fusion has begun in their cores, and there is a sort of scenario for nuclear fusion to begin, and that's when the core of the star, so inside the star, the core reaches 15 million degrees Celsius inside the core, and then nuclear fusion will begin. So nuclear fusion, okay, is hydrogen, the element hydrogen, which the star is mainly made of, fusing or sticking together to form helium and energy. So all the main sequence stars, including the sun, fuse hydrogen in their cores. The product of this is energy, mainly in the form of light, some thermal energy too, because obviously it emits some heat, doesn't it? Thermal energy. This can be done on Earth, but it's a clean process and does not produce waste. So people are trying to do this on Earth, but it's difficult because you need a really, really intense pressure to do this. Okay, so it needs heat and pressure. Funnily enough, the pressure is actually harder to achieve on Earth than the temperature, because it needs a container to withstand that pressure. So inside the star, that's not a problem, as obviously you've got, it's absolutely huge, the star. Think of how big the sun is. It's over 1 million times the mass of the Earth. Okay, it's got a lot of pressure in its core. Okay, but so we are yet to achieve nuclear fusion on Earth, which gives out more energy than we put in. We have done it on Earth, but we're putting in more energy than what we're getting out, which is not going to be useful to power anything. Okay, so what happens when the hydrogen runs out? So when a main sequence star reaches the end of its life, so the sun will reach the end of its life in about 5 billion years. So we've got a while yet, so you don't have to worry about anything immediately. The sun's quite stable. Okay, that what will happen is that the outer layers will puff out. Okay, and it will start to burn heavier elements than hydrogen. So when it formed helium, helium will stick together to form lithium, carbon, boron. If you look at the periodic table, it will fuse elements up to carbon, our sun. Some stars can fuse heavier elements depending on their size. The bigger the star, the heavier the elements it can fuse, and the limit is iron, but we'll get on to that. Okay, so depending on the original size of the star will become a red giant or red supergiant when the hydrogen runs out. So the sun will become a red giant, but some stars much bigger, like Betelgeuse in the sky, Rigel and Orion, will become red supergiant. Actually, Betelgeuse is already a red supergiant. So Betelgeuse is a red supergiant in the sky at night. You can see it in the constellation Orion. It's a huge star. Okay. And the sun, the sun will become a red giant in about 5 billion years, and it will destroy Mercury and Venus in the process, but nothing to worry about today. It's quite a long way off. Okay, so this is an overview of the life cycle. So we've got average star, we'll take that as our sun. It will form a red giant. Then after that, it just loses, it doesn't explode. So the sun won't explode. It just loses its outer layers to space, and it forms something called a planetary nebula. That's nothing to do with planets, and confusingly named like that, because the only reason it's called that is that when you look through a telescope, it looks like a planet because it's round. That's the only reason. Don't have to worry about. There's no actual deeper meaning to that. So when people first found them, they thought they were planets. It's a long time ago, but now we know they're the outer layers of stars. Okay, and what's left is a core of the star, called a white dwarf. So that's the end point of the average star. So with a massive star, like that star there, and the blue star, it will form a red supergiant, like Betelgeuse. So Betelgeuse was already a big star to begin with. Then it will explode in a supernova, which we'll talk about on the next slide. Okay, and then you'll be left with very interesting objects, a neutron star or a black hole. Okay, you're getting on to those. So we need to make a supernova, you need about 10 times the mass of the sun. Okay, so nuclear fusion goes on inside the star, fuses heavier and heavier elements, until you get to iron. So once you get to iron, like the metal, same thing, it causes the core to collapse because it can't fuse it can't create energy anymore, and so gravity just collapses the star on itself because there's no pressure from radiation pushing it out. So they are so bright, very spectacular things. So they're so bright they can be as bright as a whole galaxy they are in for a few weeks. So there's one on the edge of this galaxy here. This galaxy is very beautiful, isn't it? There's one on the edge of this galaxy, and that's one star. Okay, that's the whole galaxy. That's one supernova. And then what's left? On the left-hand side is something called the Crab Nebula. Again, it's just it's supposed to look like a crab. Don't know if it does. It's called supernova remnants. So it's little layers of the stars as exploded and blown off into space. Again, they're very pretty things. A supernova remnant. Okay. So what do we have left over? So we can have a neutron star left over. So it depends on the mass of the original star again. Everything depends on their mass. So between 10 and 25 solar masses. But again, this is an open area of research. This can be changed slightly in the next few years, but in the case of learning, that's fine for us to learn at this level. Okay, they'll leave behind a neutron star. Okay, so this is what it would look like if you were a planet orbiting a neutron star. They emit extremely powerful radiation, and pretty much anything on that planet wouldn't survive it. Okay, they also have the most powerful magnetic fields in the universe as well, and they are the densest objects. So if you manage to get a spoonful of neutron star material would weigh thousands of tons. If they rotate, they're known as pulsars. You've probably heard of that word pulsar, a watch company. I think other things called it, because what happens is a neutron star spins very regularly, and they're good at what's called good timekeepers. The pulsar, so it spins. Some of them spin several hundred times a second. Okay, some of these imagine stars spinning that fast and emitting lots of radiation. That's a pulsar. Okay, and then you've all heard of a black hole. So stars that are over 25 times the mass of the sun will leave behind a black hole. So it's not a very good name for it. It's a bit misleading because they're three-dimensional. So they appear as black because light can't escape their surface. They're a sphere. Okay. The escape velocity of the black hole is greater than the speed of light. Yeah, that's why they appear black. So it's not known whether black holes lead to another part of the universe or another universe. They're very interesting objects. Okay, so we don't know actually if you went into one, we don't know where you'd end up, and it's a very interesting thing to think about. Okay, so we're going to look at some questions here. Okay, to review. We've talked about a lot of things, so there's a lot of things to review here. Of course, it's a video, so you can pause and look back at things, which I'll encourage. That's why these questions are here. We look for a lot of things fairly quickly, so sort of pause here, and I'll let people sort of pause the video and write these things down. I encourage you to write them down in full, and then we'll go through the answers in a moment. Okay. So what is the name of the diagram that shows stars of different colours and points in their life cycles? If you went right back to the original slide, I'm going to go really quick. Here it says it's a Hertzsprung-Russell diagram. Okay, the Hertzsprung-Russell. It's named after two people. Okay, what type of star would the sun be classified as? A G2 yellow dwarf on the Hertzsprung-Russell diagram. Number 3, what is a nebula? So we said a nebula was a huge cloud of dust and gas. Okay. Number 4, what causes a nebula to collapse into a protostar? Gravitational attraction, so gravity pulls it together, if you remember. 5, what energy transfers occur in a protostar? Gravitational to thermal kinetic and light sometimes as well. Okay, but it's thermal kinetic are creating the light there. Number 6, what process has to happen inside the star for it to be considered on the main sequence? A nuclear fusion has to happen. 7, what element fuses together in nuclear fusion in stars? Hydrogen. Okay, hydrogen. Number 8, what happens when a star runs out of hydrogen? So for all stars, its outer layers expand to become a red giant or red supergiant. Number 9, when will the sun become a red giant? In approximately 5 billion years' time. Now, number 10, will the sun undergo supernova one day? No, the sun is not large enough to undergo supernova. Stars 10 times the mass of the sun or larger will undergo supernova. Number 11, what is the heaviest element that can be fused inside a star? So it's iron. So remember, iron, if you try to fuse iron, energy is taken in, so the star can't produce energy from it. Number 12, what are the two types of objects that are the eventual fate of a star 10 times bigger than the sun? So that would be a neutron star or a black hole. Okay, thank you for listening today and hope to see you in a future video. Thank you, goodbye.